Hey folks, all right, now we're going to do the math that involves RL circuits. So again, we're just continuing from this video. So I have this circuit here where I'm going to first move the switch to A, and now I want to know, I know what the current should be when I first move the switch to A and after a long time. Now I want to know, what about the in-between time? Okay, so we are going to start with Kirchhoff's loop rule. All right, so let's start here, and we're going to go clockwise around our circuit through through the resistor, and through the inductor. So we go through the battery, which is E, okay? Then we go through the resistor, which is minus IR, that's the voltage drop of the resistor, and then we go through the inductor, and from our first couple videos, the voltage of the inductor is negative L di dt. And we're back to where we started, so that's zero. So that's using Kirchhoff's loop rule, voltage gain, voltage drop, okay? So what we're trying to do is solve for I as a function of time. Now we have a first order differential equation. We have I and its first derivative in the same equation. So we have to do a little bit of math to get there. So the first thing I'm going to do is I'm going to get the I so there's no coefficient. So I'm going to divide everything by R. So you get E over R minus I minus L over R di dt equals 0. Okay, and if we separate variables, so I got to get rid of the time and stuff. So I am going to, let's see here. So I'm going to move the L over R di dt to the other side. So we've got E over R minus I equals L over R di dt. Now I'm going to flip everything over. So we've got 1 over E over R minus I equals R dt over L di. Okay. And finally, I'm going to multiply both sides by di. And I'll do that over here. So I've got di over 1, or E over R minus I. E over R minus I equals, and by the way, clearly I don't have this memorized, right? R dt. Okay, so we have R over L dt. Okay, so that's now we're ready to integrate. We have separated variables. The i's are on one side, the t's on the other. Okay, so we're going to integrate. Okay, now in this case, the current did actually start at 0, and we're looking to see current some other time later. Okay, time goes from 0 to t. Okay, now you have to be careful. You have to actually evaluate, especially the left side. Okay, so be careful. On the left side, we have a negative here, so it becomes negative natural log of E over R minus I evaluated from 0 to I sometime later. And the right side becomes R over L times time evaluated from 0 to t. That one's a little more boring. Okay, so what happens to our left side there? Okay, so we get negative natural log of E over R minus I minus negative natural log of E over R minus 0. And this equals R over L times T. Okay. So if we do our natural log rules, okay, we get the following. Now, what we're going to do here is we're going to, okay, we make these both positive. I'm going to multiply everything by negative 1. I'm going to make the time over here negative. So then we get natural log of E over R minus I minus natural log of E over R equals negative R over L times T. All right, so now we do our log rule. This minus this equals natural log of E over R minus I divided by E over R. That equals negative R over L times T. All right, so now we're ready to do our exponents. So we're going to I don't know what the actual verb is here, but we're going to take the exponent of both sides. So then you get E over R minus I divided by E over R equals E to the negative R over LT. Okay. And now if you multiply by this on both sides, move this current to the right side, make it positive, and then subtract all this stuff on the left side, and then get I by itself, you're going to get the following equation. You're going to get a coefficient E over R, and then you get 1 minus E to the negative R over L times T. Okay, so that is the current as a function of time, okay, as it grows. Okay. Now, notice does that actually follow what we said it should follow? So we said that when you first close the switch, the current should start off 0, and after a long time, it should be E over R. Is that what this gives us? When you plug in time equals 0 here, E to the 0 is 1. 1 minus 1 is 0. You get a 0 current to start with. After a long time, you get E to the negative big number, which is 0. 1 minus 0 is 1, and you get E over R as your current after a long time. Okay. So now, by the way, this is our new time constant. Now, when we write this, you're going to write it this way. E over R times 1 minus E, just like we did before with capacitors, we wrote negative T over tau. Okay, so tau actually equals the reciprocal of this. It's L over R. Okay, so that's your time constant. And it turns out if you take henries divided by ohms, you actually would get seconds. All right. And again, this is kind of a measure of how fast your circuit gets to its steady state current. Okay. Now, I will mention to my classes, and I've mentioned this before, if they don't ask you to do all the calculus, and you don't have to do all the calculus, there are some shortcuts you can take here. When you get the equation to this form, in other words, you get it so there's no coefficient in front of the I. Okay, this will be this, and this will be this down here. So let me rewrite it so it kind of looks like that. So what you would have here is I as a function of time equals E over R times 1 minus E to the negative T divided by L over R. That's how to rewrite this. And so the idea is this is that. Okay, so we did talk about that when we did capacitance, RC circuits. So I'm just re-showing you the shortcut for RL circuits. Okay, so in other words, if you get to this point and they don't tell you specifically you have to do the calculus, then go ahead and use a shortcut. Okay, now that's current as a function of time. What is the EMF of the inductor as a function of time? Well, we said that when you first move the switch to A, this should act like a battery pointing the opposite way of this one, trying to stop the current. But after a long time, it's acting like a wire, and the voltage should be 0 because it's a wire. All right, so how do we find the EMF? Well, I'm going to use negative L di dt. Okay, so we got negative L. And then we're going to take the derivative, and I'll use this version here. So the derivative of that is E over R times the derivative of 1 is 0. We get a minus. And then the derivative of E to the negative R over LT is negative R over L, and then E to the negative R over L times T. Okay, so that is our voltage as a function of time. So now if you'll notice, there's a lot of stuff we can get rid of here. There's 3 negatives, so we're going to end up with 1 at the end. Okay, so like these 2 will cancel, right? The L's drop out and the R's drop out, and you just simply get E, or the battery voltage, E to the negative R over LT. Or if I was writing it, in terms of time constant, you would write it this way: negative E to the negative T over L over R. Or shortcutting that, negative E to the negative T over tau. Okay, so any of those versions is okay. You'll probably see this one the most, and they'll say, okay, tau is equal to L over R. Okay, so does that equation actually fit with what we thought it should? Okay, so when you first move the switch to A, this should be negative E. It should try to stop current from flowing. And our equation is indeed, when you plug in time equals 0, you get e to the 0 is 1, and you get negative E. After a long time, E, a negative big number, is 0. This voltage drops to 0 because after a long time, what's the inductor behaving like? Well, it's behaving like a wire, which doesn't have any voltage. So our math is actually checking out here. Now, finally, they might ask you to graph stuff, okay? So if I were graphing, there are three things that could have voltage here, okay? So for voltage, there is the EMF of the battery, which never changes. It's boring, right? And then you have voltage drops. You have the voltage of the inductor. That starts off at negative E, so that's negative E. That's the voltage of the inductor, and it decays towards 0. So that's EL. Now, how about the resistor? Well, when you first close the switch, the current's 0, so the voltage will be 0 for the resistor, okay? And after a long, long time, it will become, this is E of the resistor, or voltage of the resistor, it'll become negative E. Now, by the way, no matter what time you pick, this will equal this plus this in magnitude. In other words, all three of them add together always has to be 0. Okay, so that's voltage as a function of time for the resistor. And actually, I should probably write this one V sub R. Okay, but anyway, that's the voltage as a function of time for all three components. What about current? Okay, well, first of all, these things are all in series, so all their current has to be the same. So if I graph current, the max current is simply E over R. When we first moved the switch to A, the current was 0, and the current will simply grow. It'll decay toward that value. And all the currents in the battery, in the inductor, and in the resistor, they all have to be the same because all three things are in series. Okay. Now, in our next video, we will move the switch from A to B and look at this bottom part of this, and like while the current's decaying to 0. All right, so I hope that video was helpful, and thank you very much.